Okay, dear Ham, so I have explained all the things I did on this radio, and I hope it wasn't boring. I want to give more details, but it will be too long, and I have the blog anyway for that. So let's just ask now what we have learned, what we have gained from this project. So maybe it will be useful to talk about that because in all the videos, people talk about only technical aspects and then just end the video. So let's ask, where's the joy for the amateur in this? Otherwise, I spent 4 months repairing an old radio. Okay, but what was the result aside from the satisfaction of it? By the way, for those asking why it took 4 months, of course, first of all, work and family life get in the way. But honestly, this was a big project. Here I explain some things in 5 minutes. For example, I say that I replaced all 10 talent capacitors, but friends, those capacitors have to be removed first. They have to be desoldered, carefully reinstalled in tiny spaces, and just when you think you did everything, you realize something is wrong. You remove the PCB again, start over. These things take time, and I worked on many issues multiple times because I'm a perfectionist. I lie in the bed at night and I say, would it have been better if I had done it another way? And the next day I try something else. So these things extend the process for me, and this is how I work. And this work. I mean, this is my first takeaway. If we want to talk about some lessons learned, the first thing that comes to my mind is systematics, the system. No matter what project I undertake, there's always one fundamental principle in front of me. As a principle, I never work on a radio before gathering enough information and documentation about it. I just don't open it up and start messing with things. I open a device only if something needs to be done. I examine it first, and I believe in lab work. This is essential. For example, I often hear things like, "This is not working," and then I ask, "How do you know it's not working?" Open the specs and check first. Maybe the device is behaving exactly as it is supposed to, but you're not aware of it, and you don't know the device, so you assume automatically that it has a problem or it's broken. Open the specs first, get some measurements, confirm whether everything is on in line with the specs, so you will understand if there really is a fault or not. And the opposite example is also very common. This works perfectly fine. And so I ask, how do you know? Bring it here, let's measure it in the lab, and then, let's check it with an oscilloscope, with a spectrum analyzer. Are you generating interferences? Are you, emitting unwanted, undesired signals, spurious emissions? You think it's working fine, but I have the device's specs right in front of me, and come on, bring it and let's compare them first to understand if it is really good or not. So we need a reference point. And when I do research, I always focus on finding those reference points. And in this Heathkit example, we are lucky because for assembling this device, everything is provided to the ham, and we have a manual that includes assembly instructions, calibration, and even basic troubleshooting. And fortunately, some amateur friends scanned and uploaded all those documents to internet. So the manual for this device is 155 pages long, and to be honest, I've read it all. You might ask, why did this project take 4 months? Well, that's why, because without doing all this research first, all this analysis first, you don't learn anything. Okay, and of course, almost half of the manual is about where each component should go. And since I didn't assemble the device from scratch, I was able to skim those parts quickly, but I still took a look at all of them to familiarize myself with the circuit boards, to get acquainted. And then the manual explains how to perform all the calibrations. It details the exact order in which adjustments should be made, what to pay attention to, key points, troubleshooting. For example, if a specific part of the circuit isn't working, the manual lists common issues an amateur may, encounter and may not realize. So they wrote down all those possible problems. And if you read all this carefully, you really understand the device, right? Really understand the radio. Okay. This manual explains everything: transmitter, oscillator, receiver, every section's working. All the components parts are provided, so if you break or lose something, you know exactly what to look for, where to look for, in the market. And all of this is very, very important. And of course, additionally, the manual includes a very well made circuit diagram. And Heathkit didn't stop there. They also give you a mechanical assembly guide. So this one shows all the physical layout, all the parts in the chassis, where each cable bundle should connect, how the grounding should be done, and in case, for instance, you want to, put the radio in a car, install it in a car, they even give you guidance on that, to make it the correct way, the groundings, how to install it in the dashboard, how to fix it, etc., etc. So all this information is here. By the way, at this point, let me open a parenthesis. So if anyone feels offended, that's fine. I don't care. If one calls himself an amateur, herself an amateur, and if she has a real passion for RF electronics and spent some time learning about it, then that person should have no problem working on this radio with all this information. And if they you know if you call yourself an amateur, and when you have all this information available to you, and if you can't fix this radio, to be honest, you need to sit down and study more, because maybe the problem is with your level of knowledge, and that's what you should question. The document contains everything, and anyone who genuinely enjoys radio electronics should be able to fix this device with all that much information. So let's get back to the main point now. So the first step is gathering information, and whenever, to be honest, I skip this step in any project and I rushed into things, I ended up breaking something, and I put long time to fix it. The second step is confirming if there's actually a fault, a problem. If something seems to be working, is it really working? We, check using references and measurements. So look at the schematic now. There are all those values noted in red. These are my measurements against the values given by Heathkit on the schematic. Okay, voltage, what should expect, what should measure. So before starting the project, I measured every point on the circuit board. So that's why, again, it took me 4 months to finish the project. So I checked the receiver, transmitter, VCO, every single stage, and I spent several nights doing that because I wanted to know if there were any hidden problems. Okay, I didn't want to miss anything, and thankfully, I didn't find any major issues, and device is solid. And another key principle, so that's another principle: always measure first, and this should become a habit. And while working on device, I realized something else. I forgot much about the FM modulation. I had studied some when preparing for my license exams, etc. But since then, I always worked on AM. Mostly CW, SSB, and I hadn't really done much with FM. So, for example, this project reminded me the FM quieting phenomenon. When a powerful signal is received, an FM radio suddenly becomes silent. Okay, and that was something I'd never tested myself in real life before. So I had the chance to experiment with that. This circuit allowed me to do some FM quieting testing and experimentation. So something else I learned in this project. So this radio is PLL controlled, phase locked loop, and a PLL system works like this: you have a reference signal, and your circuit's frequency is continuously adjusted, corrected based on this reference signal. So let me show it on the diagram. So this is the radio's VCO, voltage controlled oscillator. This oscillator, by the way, does not generate signals directly in 2 meters band. Instead, it produces a lower frequency around 22, 23 megahertz, which is later multiplied by 6 to reach the 2 meter band. Why? And the reason is simple. Generating 145, 146 is difficult, and at such high frequencies, small variations in components can cause instability. So instead, the circuit generates lower frequency, which is later multiplied, and therefore the lowest frequency you use in the beginning, the better, the more stable your oscillator will be. So for receiving, I'm talking for receiving as an example, this VCO produces 22.5 megahertz at 146. Then this signal is processed further. It's mixed with another oscillator, an offset oscillator, with 21.5, and the result is about a signal that is around 1 megahertz, lower frequency signal. This signal is then divided with, and processed by the PLL circuit. The circuit compares the divided signal with a stable reference frequency. And if there's any difference, then the system adjusts the output or the receiving frequency accordingly. For 146 megahertz, the required comparison frequency is 833.333 hertz exactly. And this reference frequency is generated by the master oscillator, which was 10 megahertz, which I showed you in my previous videos. The signal coming from the master generator is divided by 12 to produce 833.333 hertz, and the signal is sent to the phase detector. The phase detector compares the two signals. If there's a phase difference, then it makes a correction. And how does it do that? Um, it adjusts. Actually, there's a varactor diode in the VCO, a varicap diode in the VCO. If there's a phase difference, the phase comparator changes the voltage to the varicap diode in the VCO, and this fine tunes the oscillator frequency. So that's how the whole process works. I of course simplify it a lot, but in reality, it's more complex, and yet it's a very effective system. And I am really impressed by how well it works. Before working on this, I didn't fully appreciate PLL circuits, and now I know that with a very low reference signal, such as the 833 hertz, you can control an oscillator at 22 megahertz, and it works incredibly well. The circuit locks in 50, 100 milliseconds, and at the end it doesn't drift at all. As long as the voltage remains between 10 and 16 volts, the frequency stays rock solid. I found this really impressive, and this was my first hands-on experience with a real PLL circuit, and it helped me understand how it functions in a practical case. Of course, in back in 1975, there were no DDS modules, DDS chips. People just could buy and install DDS chip, digital synthesis, frequency generator, and they had to rely on analog things for frequency control. And even so, 50-year-old device still has incredibly stable frequency generator, and it was a great learning experience for me. Apart from that, I don't have much to add. If you made this far, I sincerely thank you. There are 4 videos to watch. If you watched all those parts, well done. And if you have any questions, feel free to reach out to me by email or other channels. If there's anything I can help with, I will do my best. So I send you my best regards to all from Montreal, Canada. Of course, my heart is in Istanbul, Turkey. But life goes on. Take care, and 73 to all of you. Thank you again for watching.